Hello everyone, and welcome to our video presentation. If you were one of the 1 billion TV spectators who watched Michael Phelps win his 14th Olympic medal, or have cheered for the British diver Tom Daley achieve his bronze, you must have taken notice of the place where all of this has happened, the London Aquatic Centre. The centre, which is located inside the Queen Elizabeth Olympic Park in East London, was built specifically to house the aquatic events of the London Olympics in 2012. Late famous Zaha Hadid was the architect behind this structure. She said it was inspired by the surrounding environment. The structure is irregular in shape, with an average height of 45 meters and a footprint of 1,200 square meters. The construction contract was awarded to Balfour Beatty in April 2008. The centre was completed in July 2011, costing around £250 million. But after the Olympics, it was modified and reopened to the public in March 2014.
The integrated structure form is hyperbolic curve form, which makes two different curves into different directions, one bending from north to south and the other from east to west. Basically, the integrated shape is just like a Pringle shape. Look at the north-south axis of the building. The ceiling picks up, dips down, and picks right back. Below the ceiling, you have the big Olympic pool and the deep diving pool. So the ceiling gives you two separate spaces for the two separate sports, the same as the east-west axis of the building. So you have combined north-south and east-west together. You have one space that's great for having sports events, but also great for viewing them. The structural hierarchy can be divided into main, secondary, and tertiary. The main support system basically can be divided into two parts. The transport truss is supported by two reinforced concrete coils. The vent truss is supported by a reinforced concrete wall. For secondary, the architectural roof geometry was inspired by the full geometry of water in motion. For tertiary, the permanent roof is a warm roof construction created by insulated cladding on the top and timber cladding facing the pool tank. The chosen site was close to the river. This means that the topsoil, which would normally carry the load, had aluminum overlying land-based clay and the sunny sands at depths, which is classified as poor ground conditions. The problem engineered first was the presence of the surface tunnel, which means that the pile will not be able to reach the required depth in this area. Therefore, they carry out detailed finite element analysis of the tunnel, ground, and the pile loads. As a result, they developed this ground transport structure to span over the tunnels. This means more concrete needed to be cast, but also means that the foundation will be constructed safely without disturbing the tunnels. They use a technique in casting this pile called the continuous file auger, which is basically a machine that bores the ground going to the required depths and pour concrete in place while going out. This will avoid the potential need to bore and sleeve each pile, reducing the needed time and cost for this operation. For the roof, since it's a very long free span, which means very high bending forces on the truss member, they adopted steel for main material for its high strength, good toughness, and good stiffness. Similarly, for the supports, they needed a material that will transfer the loads from the roof to the foundations. This means a huge compression force. Because of the high compressive strength of concrete, the superstructure adopted concrete as its main material. Also, roof structure is fully cladded by aluminum and features a timber soffit to its underside. Because of the fact that aluminum can resist corrosion more than steel, it's a lot lighter in weight, which decreases the load on the truss over the long spans, and also because it looks better. The final structure comprises brass steel frames made out of standard universal beam and universal column section, with all bolt connection to enable repeat erection and later disassembly.
There is a clear load path. The load applied on the roof will be transferred through the chassis to the concrete supports and then to the foundation on the ground. Look at the superstructure. You can imagine that an eagle. It has wings, the wing area of the roof, body, the central area of the roof, and feet, the concrete supports. We can see that it's symmetrical, thus the center of gravity is on the central axis of itself. The building has two turn-up wing areas on both sides, which cause compression to the central area due to gravity. A compression hoop is formed around the central areas. Designers have to use cross ties, which can carry tension to balance the structure. When the roof was built after supports were finished, it started from the middle. When the central area was completed, the force which the wing area would provide later to balance the structure was not there, so designers need a temporary tie to bind the two columns to ensure safety. All the trusses are formed from fabricated edge section to ensure local instability will not happen in all elements. The roof has an aerodynamic shape, which decreases the area in direct contact with wind, decreasing the stress caused by the wind force. When wind comes, it will attempt to overturn the roof. The bearings on the leeward side will carry more compression than the windward side. The wind will also cause deflection to the roof. The slight bearings on the wall are designed to reduce the impact of temperature change, and they contribute to reducing the deflection caused by wind as well. Snow is also a necessary concern. Snow has two effects, one which is gravity load, and the other is the melted water effect. Thickness of accumulated snow can be used to measure the snow load. It depends on the snow and wind both. In this structure, both ends of the roof are lower than the middle, which can let the snow slide down. The second effect is ponding, which is water that results when snow melts. The gutters on the roof are designed to drain this water. From the map, we can see that London is in low seismic area. As we see, the building is near a river. The piles will carry compression under normal circumstances. In the extreme case of flooding, the underground water level will rise, which will cause buoyancy, and if the pools are empty, the buoyancy will be higher. The piles are designed to resist tension in this case. Fixed and sliced vertical bearings are used to transfer loads from roof to supports to resist thermal expansion and wind load and earthquake as well. Bolted connections were used in stand trusses and roof trusses to transfer load from one to another. In order to build this single-span roof, scaffolds resting on the ground were used during the construction. This hindered the construction of the swimming pool. Due to the time limit, the construction of roof and pool must be operated at the same time, so builders had to build and remove the scaffold every day, which is not practical. The working radius was only about 100 foot because the stands will be built between the river nearby and the aquatic center. The chassis of the temporary stand were heavy due to the large span. Thus, more balanced load was needed, and this doubled load on the ground.
Now we will discuss the relationship between the structure and the environment. We think that it fits well because the roof flows like the nearby river, and the surface area was covered in grass to integrate the structure into the surroundings. Then we discuss how the structure affects the environment through three aspects. First, the embodied carbon emitted in the use of the construction materials. There were efforts to reduce this by using 75% coarse aggregates in the concrete and by replacing Portland cement with 40% of a recycled material called GGBS. The use of a natural building material like timber is also good. However, the fact that this timber was imported from Brazil meant high unnecessary carbon emissions in transportation, and also the use of aluminum in the ceiling, which has a very high embodied carbon, was a negative point. Secondly, for the manufacturing and assembly processes, as discussed, efforts were done to minimize the disturbance of the environment during construction by making sure that first, the service tunnels below the piles are safe, and by locating the mobile cranes in a safe distance from the riverbed. Finally, the need to light and heat such a huge space is very energy intensive, but some efforts were also put to reduce this by having natural lighting and reducing heat escape from the roof by insulating it well. Grey water was also used to irrigate the grass. A last point to note before commenting on the overall evaluation of the sustainability of this structure is that structural sections were utilized beyond the specified code percentages, which meant reduction of unnecessary material use. Overall, this structure has a high carbon footprint, which is a negative thing, but it could be argued that this effect is shadowed by its huge social impact. This landmark made a rural part of London attractive to visitors, and it is now used constantly by the locals, so it helps a lot in the development of the neighboring community.
This part are architecture comments and our judgment. As explained, the building is considered sustainable and well fitted to the surrounding environment. From the inside, the building looks spectacular. The curtain walls and openings in the ceiling provide natural light to reduce the need for artificial light and heat. In fact, the whole inside experience is great, with the curtain walls allowing for natural light inside the pool. The concrete fair face finished surface giving a natural feeling as well as the wooden ceiling. Apart from the technical accomplishment we explained before, to measure the success of the structure, it's enough to say the great reviews both as a national landmark by local community and spectators from all over the world at 2012. The building is regarded highly by architects and was shortlisted for the Rebel Sterling Prize 2014. However, a famous incident happened is that some spectators were not able to see the diving contacts from their seats, and this because of the narrow angle and from the suspending ceiling, which could have been resolved by increasing the height. Finally, we think the building is successful, but there are still some points which we think were shortcoming in the design of the structure, and we will discuss some alternative solutions. The north-south dip in the ceiling, which is intended to be an invisible curtain separating the diving pool from the main pool, was really an artistic touch that didn't show any significance in the interior of the structure. It only prevents the structure from having one curvature in the direction, which could have been replaced by a whole arc of fabric structure. To form the roof, each member needed to be specially made, so this added the complexity of the manufacturing, the assembly, and the construction of the project and cost. Instead, maybe the section could have been standardized. As discussed in the sustainability part, the use of the imported timber and aluminum caused the embodied carbon to increase. Instead, steel or any other local materials could have been used.